In this session, we talk about the scale-up problem with mixing and agitation equipment. Design of a mixing equipment may involve a set of experimental data, and those data may not be available for the large-scale equipment. So typically in a laboratory setting, experiments are performed and those data are obtained. Now there comes the need for how to perform scaling up, because the experimental data are for lab scale setup, and then we need to design an industrial scale mixing and agitation process. Now the scale up may have different purposes, and so there may be different and very diverse requirements. Now one concept is what is called this geometric similarity. It's important, also it's simple to achieve, meaning that you can have a certain ratio of the impeller diameter to the tank diameter, and then when you do the scale up, you maintain that ratio. That's a simple process. However, there are other similarity that may need to be maintained. For example, the kinematic similarity, meaning that the ratios of velocities and mixing time, they may need to be maintained. Another concept is what is called this dynamic similarity. What it means that it may be required to maintain ratios of viscous, inertial, and gravitational force. Now, even geometric similarity is achieved easily, it may not be possible to achieve both dynamic and kinematic similarity at the same time. So there is a trade-off and what you want to achieve, and that depends on the particular applications that's under consideration. Now for a particular process, there may be different requirement, and that's why we may need to consider different scale-up operation. So for example, for a certain process, you may need equal liquid motion. That's the velocities in the small scale and in the large scale process should be maintained the same. For example, for blending operation, this may be a requirement. For other cases, you need to maintain what is called this equal suspension of liquid. Also, when say mass transfer is involved, equal rate of mass transfer may be one of the requirement. And through theoretical analysis, it can be shown that equal mass transfer is obtained when the power per unit volume remains the same. So these are different scenarios that you may need to consider when scaling up for a particular mixing and agitation equipment. Now, what needs to be considered when you are performing a scale up? We describe here a simple 4-step procedure. Step 1 is to calculate the scale up ratio. Now, this scale up ratio is defined as the cube root of the volume ratio for the final and the initial conditions, meaning if you have an industrial scale operation, if you have the volume to be V1 for the lab scale and V2 for the industrial scale, so R is defined as V2 over V1. This ratio, it's cube root. We know that typical standard ratios for different dimensions are maintained. So if you have dA1 and dt1 and dA2 and dt2, those denoting the impeller diameter and the tank diameter respectively, then V1 can be obtained as pi d1 square over 4 times h1, where dt is the tank diameter and h is the level of liquid in the tank. So we have V1 to be pi over 4 dt1 square times h. We know that it's a standard to maintain the level of liquid equal to the tank diameter. So if we simply plug in there, we get V1 equals pi dt1 cube over 4. Now V2 over V1, then we have pi dt2 cube over 4 over pi dt1 cube over 4. Now we know that also the ratio of dA is also maintained as a standard. So as the tank diameter increases, so the impeller diameter. dt2 cube over dt1 cube is equal to dA2 cube over dA1 cube. So we get R equals V2 over V1 cube root, which becomes simply dA2 over dA1. So that's the definition we'll be using. Now you may ask, why are you expressing in terms of dA? That's because typically standard ratios are maintained compared with the impeller diameter. So that's why we're expressing in terms of the impeller diameter. You have seen the equations. Most of the equations are developed based on the impeller diameter. Now step 2 is when you get the R, other dimensions can be calculated, meaning that dt2 is simply R dt1, h2 is simply R h1, and so on. The step 3, which is important, is to determine the agitator speed. And for this case, we have n2 over n1 becomes 1 over R to the power some number eta. Now this eta depends on what you really want to achieve. So if you need an equal liquid motion, eta is 1. If you need equal suspension of solids, eta is 3/4. If you need equal rate of mass transfer, eta becomes 2/3. Later we see how this number came from. However, we are not going to details about the other two. Those can be theoretically obtained. Now step 4 is when you know N2, you can calculate the power requirement because the power equations involves the use of this rotational speed. Now the previous equation shows if you get the scale-up ratio, you can calculate the speed. Now what if the speed is to be remained constant? Now in this case, let's consider turbulent flow. We can express the power in terms of kT n cube dA5 rho. So now volume is proportional to dA cube. So if we divide both sides by V, so P over V will be some constant times dA cube. We'll have this kT and that constant will become C, another constant, and n cube dA square rho. So that's an expression for power requirement per unit volume. Now if you have the large scale and the small scale, and for which you can get P2 over V2 over P1 over V1, that will simply become C will cancel out and we'll have simply n cube dA square, that ratio. And if we separate these two, it will be simply n2 over n1 cube and dA2 over dA1 squared. Now if we want to maintain n2 equals n1. So in that case, the ratio of power requirement per unit volume will be dA2 over dA1 squared. Okay, so that's how you calculate the power requirement when the rotational speed remains the same. On the other hand, if the power requirement per unit volume is to remain the same, meaning that for this case, we want to maintain equal mass transfer, and we have shown earlier that equal mass transfer means you need to maintain power per unit volume to be the same. So from this expression, if you get the power requirement per unit volume to be the same, meaning this ratio becomes 1, this entire side can be written as 1, and from there you will get n2 over n1 to be dA1 over dA2 power 2 over 3. Now that's the expression really we're talking about. Say here that when we have equal rate of mass transfer, the constant eta becomes 2 over 3. Now another term is the time requirement. We know that if the other dimensions are maintained constant, the term ntt it becomes constant, meaning that n2 tt2 will be n1 tt1, and from there we can get, for this case, we'll have tt2 over tt1 simply becomes dA2 over dA1 power 2/3. To remember that here this is dA1 over dA2, this is dA2 over dA1. So we have seen how to perform a scale up, how to define this scale up ratio, and how to calculate the power requirement for an scaled up mixing and agitation unit.